Okay. Hi, I'm Mike Stone, and I know people are still logging on, but Marcus uh, asked me to get the conference started off. So I'd like to welcome you to the 5th Gateway NMR Conference. It's a little bit different than the conferences in the past in that it's virtual due to the present circumstances of which we're all too familiar. So we really miss you. We're sorry that you can't be in Nashville with us this weekend. We have a lot of things to do, and if you've been watching the slides, hopefully you can come back to Nashville in the near future when things are better and enjoy some of the many amenities our city and area has to offer. I want to give a particular shout out to the organizing committee, and particularly Marcus, who have done a tremendous amount of work of getting this conference put together, and more than that, actually transitioning it to a virtual meeting, which, as you can imagine, it has required a considerable amount of effort. So great job, Marcus. All right, now let's see if I can advance my slides. I also want to just give a shout out to the Vanderbilt Center for Structural Biology, which was established approximately 20 years ago here at Vanderbilt and has really been a catalyst for building research in structural biology and interfacing structural biology with chemical biology and molecular biology and biomedical research here at Vanderbilt and Vanderbilt University Medical Center. So the Center for Structural Biology houses not only our NMR resources, but also all of our other structural biology resources at the university. And so it's really an integral part of structural biology efforts here at Vanderbilt. And it's been headed up by Walter Chazen for the first 20 years of its existence. So I know there's a number of students in the audience, and if you're interested in opportunities for graduate or postdoctoral research at Vanderbilt, I encourage you to log on and check out what's going on here at Vanderbilt with respect to structural biology. Okay, so the Gateway NMR Conference, this is the 5th iteration. It started in 2016 in Louisville, Kentucky. And the conference was originally envisioned to be a regional conference for NMR spectroscopists in sort of the Midwestern area of the United States, which I have sort of circled on this map here by drawing a circle of some radius around Louisville. And I thought I had to at least make sure St. Louis was in there because we have the Gateway Arch here. And as you know, so the idea is the Gateway is the entrance to the great western expanse of the United States. And I think that's a good metaphor for the Gateway NMR Conference, that our research is extending into the unknown of the future. Okay, so we're in Nashville this year, and next year we will be in Oxford, Ohio at Miami University. I'd also like to thank the organizing committee members for helping us put together this conference. Okay, so we have, I think, a really exciting program beginning in a few minutes. We have, I'm really excited about the presentations from Clemens and Amy at Bruker Biospin. And then after the Bruker presentations, we're going to move to posters. We have a number of exciting posters that have been submitted by students and postdocs from throughout the region. And we've selected a number of flash talks to to start out, and then move into the actual poster sessions where you can actually talk to some of these individuals on a Zoom conference. Then after the poster session, we'll be having a roundtable discussion moderated by Raphael Bruchweiler with, I think, interesting topics that are of contemporary interest in NMR spectroscopy. For those of you who are monitoring sunset tonight, in Nashville, I'm told the sun goes down at 6:49 p.m. And I believe we should be finished with the evening talks, at least before sunset here in Nashville. We'll start up again tomorrow morning, bright and early, and at 8:30, and we have a number of great talks scheduled tomorrow morning, highlighted by a keynote address by Rich Kowalski from St. Jude Children's Research Hospital in Memphis. And I'm sure Rich will update us on the exciting new developments and addition of new NMR spectrometer down the road at St. Jude. I should mention St. Jude is about 200 miles west of here. For those of you who aren't familiar with Tennessee geography. So we have actually quite an active NMR community here within the state of Tennessee. Okay, then we'll take a lunch break, and we have two final sessions tomorrow afternoon. Ending up with Mike Kennedy, who will be hosting the conference in 2021, as I mentioned, in Miami University in Ohio. And I should also mention we will be recording the sessions, so if anybody needs to miss the talks tomorrow and wants to get a recording of some of them, I'm suspecting that we should be able to do that. Okay, finally, a little bit of housekeeping information. We're going to be on the same webinar link the entire conference. So if you log out and log back in, use the same link, and hopefully that will work. It should be the link you received when you registered for the webinar. We'll be trying to keep the speakers on time so that we don't overrun time. And so if you're a speaker and you get interrupted by the session moderator, that's probably what's going on. You're running out of time. I'd ask the panelists to please mute themselves unless they're participating in the discussion. This helps keep extraneous noise out of the background. And questions during the sessions, use the Q&A link. You should have a Q&A link at the bottom of your Zoom webinar screen. And we will be answering questions after the speaker. I believe there's also a raise your hand feature, and we'll try and monitor raise your hand questions as well. But just go ahead and type questions into the question and answer link, and the session moderator should be monitoring that. Okay, so one of the things about a virtual meeting is you can get comfortable, grab some coffee, some snacks. I don't have to tell you where the bathrooms are. And enjoy some great science this afternoon. And with that, Marcus, I'll turn it back over to you.
Okay, thank you, Mike, so much for this. It really is a great pleasure and honor that we have Bruker here to represent the company and give us some news or introductions and some knowledge about their products, primarily the NMR software. And I'm particularly excited to introduce now Clemens Anklin. He's the vice president of NMR applications and training at Bruker in Billerica. He's been there for, and when I saw that, I really kind of had to think twice, for 32 years. Is that correct, Clemens? I think he's muted.
Unmute. Yes, this is correct. Actually, 32 years in the US and 4 years in Switzerland.
Right, so I've been with the company for 36 years altogether now. Clemens got his PhD in Switzerland at the ETH, the Swiss Institute of Technology. And then pretty much right after that, he joined what was SpectroSpin at that point. He's been, as I said, with Bruker since then, and then in '88 moved to Billerica. So Clemens has been in Billerica for quite a long time and acknowledged a lot of experience and knowledge. And really, he is the go-to person for almost any question related to NMR. I've had many of those help sessions from him already, and I don't remember that he ever had a question, or that I ever had a question that he couldn't answer. Today, Clemens is talking about advanced 2D and 3D processing, tips and tricks and unknown features. Actually, just about this last week, I had a student here, and the student was totally unfamiliar with topspin processing, and we kind of went through that quick, and the student was really kind of amazed how easy it was to process a 3D spectrum compared to some of the other tools that they've been trying to use. So I think what this lesson will give us is a deeper understanding in how powerful actually topspin is in processing 2 and 3D or even higher dimensional spectra. So I'm really excited to hear what Clemens has to present, and would like to welcome him and pass the baton to him.
Thank you very much, Marcus. Thank you for the very kind introduction and setting the bar so high for me.
Well, I don't think it's high.
It is.
It's just reality.
So let's switch over, and yep, I got the right screen share. Always is the question between the different online organizations, or Zoom and Teams and WebEx and all of that. They're all similar, but not quite the same. So anyway, let me get started. So what I'd like to go over this afternoon is a bit lighter. It's not high-flying science. You'll hear all about that tomorrow. So we will go beyond the basic processing operations. We want to look at options which are available, and I will demonstrate ways to visualize what's going on in various processing steps, because for a lot of people, the processing data is a black box, but the tools are actually there to break it apart and look at what's happening. There are a few tips and tricks, and I'll also have some features in there which are on the lighter side. It's fun with data. Some of that, what the contents here, it was also, I already presented in our webinar series, which we have done now throughout this pandemic, and which is still going on. You'll find the link at the very end of this presentation. So we want to look at options for the processing commands, 2-dimensional, advanced 2D processing options, quick look through a bit of the analysis, then we go into 3D, and there are tips and tricks interspersed all the time. So everybody's pretty familiar with the standard processing. You take some time domain data, you have a series of FIDs, you give the magic command, and you end up with a spectrum. So in this case here, the software actually does things for you in the background. So you define a window function, it applies that if you have phasing the phase correction mode that is used, baseline correction mode that is used without you having to give extra commands for that. And also linear prediction is implicit. If the parameters are set, it will do it. This is in contrast to 1D Fourier transform, which only looks at part of it, and apodization and phase correction need to be called separately. So for quite a number of users, the fact that linear processing is used in the data is just black box. It happens and you don't worry too much about it. The Fourier transform mode, FT mode, is also an implicit parameter that you ask for a Fourier transform, you get one, and the correct Fourier transformation is chosen from the acquisition parameters, whether you have real or complex data, whether the mode in the indirect dimension is magnitude, states TPPI, echo, anti-echo, states, or whatever methods are available. Now, there are commands available to break that all up. So instead of XFB, Fourier transform both, you can do Fourier transform along the F2 dimension. You then see a stack of spectra. So they're time domain along the F2 at the acquired axis. There's still frequency domain along the acquired axis and their time domain in the indirect dimension. You see your amplitude modulation or your phase modulation. You also get an idea on how fast signals decay. And this is often helpful when you work with large molecules. You can do a quick XF2. And if you still have signal at the end of your experiment, linear prediction is going to do something. If it's all decayed, well, linear prediction cannot predict nothing. So it's not good for anything. I also often use it to just get a quick idea, let's say in a spectrum, in a HSQC, how fast do my alphas decay? If they decay really quickly, my HNCA or HNCACB is really going to be difficult to run. So we do then the XF1. So XFB is a combination of XF2 and XF1. You can actually also do it back, the other way around. You can do the indirect transform first. It will warn you that you haven't done the F2 transform, but it will do it. And you now see a set of frequency domain in the indirect dimension and basically the FIDs in the direct dimension. The reasons for doing that is, as I mentioned, to get an estimate of the decay rate, or I want to perform an additional operation between the two steps. So you can do a baseline correction between the two steps. And this is actually really a good thing to do when you use linear prediction, because often the distortion from the water is periodic, and linear prediction likes things that are periodic and just predicts it out. Options for all of these commands is, for example, once you have determined the phase correction, you don't need the imaginary parts anymore. So you can give it the N option, XFB space N, and it discards the imaginary parts. And it stores just the real part. You can always restore that with the Hilbert transform. And if you've forgotten that for years, use the command DELI, delete imaginaries, to remove probably or clear up about 75% of your hard disk. So other options we have for those commands, this is especially interesting if you want to compare 2D data sets in an absolute way on what their intensity is. For it, spectra are always being scaled after Fourier transformation, so they fill the available data size. And of course, if spectra are scaled differently, they're hard to compare to each other. But you can fix the scaling factor, so you can tell it what scaling factor to use, and that makes it a lot easier to compare data sets. Now, if you want more control than that, we have a set of commands, basically the XTRF commands, which has some subcommands, XTRF2 along the F2 axis, XTRFP, to reprocess something which has already been processed. And when you use these commands, all the processing options are evaluated. So the FT mode has to be set properly, the apodization mode, the phase correction mode, the baseline correction mode, and all of these modes are executed exactly as you tell the system to do that. So for example, one nice way of, or an interesting way to do that is to observe the effect of linear prediction. So here is an HSQC of a good old standard sample, cholesterol acetate. This is acquired with 400 points. And this is XF2 with the regular parameters. This is a regular acquisition. So in order to observe the effect of the linear prediction, I set everything but the linear prediction to no. So the only thing that will be executed with the XTRF2 command is, XTRFP1 processing in the indirect dimension will be the linear prediction. And what I can see here, of course, this has now also been split in real and imaginary. So I see my 200 real points up to here. And this part of the spectrum has been linearly predicted. You can see signal, which has a frequency or a coherence, gets predicted out, and noise, which is incoherent, dies off very quickly in the prediction. So in this case here, we've doubled the data points. These are the default parameters. I can easily push that to the extreme, and I set the parameter LP bin to 2K. And in the real part, then I go out to 1,000 points. So you can see this is still a good and stable prediction. You can see that the line actually gets narrower because the sharp component is really what gets predicted most easily. So here we can see that this is still a reasonably stable linear prediction. In other cases, you can see that it falls apart, or you can see that signals which are broad from the get-go are not going to get predicted very far out. So other things you can do with, now with a second example would be NUS data. And if you do an XF2 with NUS, non-uniformly sampled data, it shows you actually the result of the reconstruction. So this is reconstructed, the missing data points have been filled in by the reconstruction algorithm. But in some cases, you want to see what actually happened in the experiment. So you can do a XF2 NUS-FT, and that shows you the FIDs where they belong with blanks in between. So the sampling schedule, the NUS list, would have the indices for the traces we see here, and the other ones are absent. So I have, this is 25%. This looks like a lot more, but it is truly a 25% sparsity here in this experiment. You can do the ND2D, and that shows the FIDs, how they have been acquired in the order of NUS list. If you type XF1 on this, this doesn't give a meaningful result because they're in the random order where they have been acquired. So another tool which is available in Topspin for data processing would be the strip transformation. And you more or less literally rip out the strip of your spectrum. So 2D spectra often contain a lot of empty space, and the strip transform lets you focus on a small area. Protein NMR is quite a good example for the lots of empty space, because all the experiments which detect amide protons typically have the right side of the water, or on the right side of the water there is nothing, with a few notable exceptions, but it's usually empty, so you don't have to kind of fill your hard drive with all that noisy space out there, and you can use the strip transform to get rid of the second part of the right part of your spectrum. This is controlled by the parameters STSR and STSI. It's the first point of the strip transform, and it's a total number of output points of the strip transform. So if your size is 1K, a strip size of 512 and the strip start of 0 gives you the left half of the spectrum. So for example, if you have a 1K by 1K square and you strip from 256 to 512, that gives you the center square of your spectrum. Whether that makes sense, just a good example. So this is what it would look like. And what you can do now is you can go and zero fill or increase the size of small portions of your spectrum massively to increase resolution when the original resolution just doesn't give you sufficient resolution, and you have cancellations, for example, here in a double quantum filtered phase sensitive COSY, because your digital resolution is equal or smaller than the actual coupling constant. So you pick a region of interest, you right click it, you say save this to the strip parameters. Then after you've done that, you increase the size massively here by a factor of 8, and the strip parameters get scaled up accordingly. And you're now transforming just XFB, and the resulting matrix is only what is in these defined limits. And you can clearly see how this has improved, whereas here we have a lot of cancellation due to the antiphase nature of the signal. And if you look at these signals here, we see every little bit of resolution, and we're probably at a level now, this year even further expanded, where we can extract at least an approximate of the coupling constant directly from this spectrum. So similarly in HSQC spectra, you do NUS, so you get all this beautiful resolution, but then you're hesitant in making large data matrices. So here I can increase the size in the indirect dimension, in the carbon dimension, to 32K. This approaches the resolution of a 1D carbon spectrum. This is NUS. The TD in the data set was 16K points. I acquire 3% of the data, and then I transform that into a 2K by 32K, but I only look at the region here because these two peaks are of limited interest in this case. So you can see what this brings. This is transformed into a standard 2K. This is transformed into 32K in the indirect dimension, and I can, 4/100ths of a ppm are clearly resolved in this case without filling the disk. We have a lot of commands in Topspin for baseline correction, and well known are correction of two-dimensional spectra, and in most cases where you work with water, the correction of the entire spectrum is not possible because around water you have a discontinuity, and there is no polynomial function of fifth order maximum which fits a function like that. So you split it into the left half and the right half, and that's much more easily fittable. And so you have a fifth order polynomial, and it's often helpful to match the distortion to the order. So here, going from original spectrum with a third order function, you flatten it nicely. With the fifth one, it overcompensates a bit and bends this edge up, so you can pass on that order. We can also, the right side of the spectrum here is a very large distortion, but there is no signal. So I can put the cut a little bit closer to the actual signal or away from the water signal, and it actually results in a better correction in this area here. So you can do that to the left of the water, to the right of the water, and there is an AU program which simply does that with one command. Now we have some, you can also use that to just clean up a strip in your spectrum. And then we have commands which are actually quite interesting to do. So it's with ABSF1 and ABSF2, you typically set the left and the right limit of the correction. If you use SIGF1 and SIGF2, which is usually used for signal to noise calculation, you can set that to different numbers. So here I set these points, ABSF1 and ABSF2 for the bottom, and SIGF1 and SIGF2 for the top. And I see these will be my limits. If I do a correction over that, I get a trapezoidal correction. Another good one is the ZE-RT, the trapezoidal erasure of data. And here, a nice example, this is a small molecule. I think it's actually stevia extract. So you have the COSY spectrum. I zeroed the lower triangle from the diagonal, and in the rosy, I did the opposite part of it. And then I use the add 2D command to add the two together, and I can create the spectrum, which is 1/2 COSY, 1/2 nosy, as a nice example here. Makes a good old ruler and pencil-based approach for interpretation possible. Here, some tricks with echo-anti-echo data. If you use the first FID for phase correction, that is usually a bit tricky because your very first FID is actually 90 degrees off with respect to the full spectrum. Because this is always a linear combination of the real and imaginary. And in order to do that, we can have the EAO option for the Fourier transform, and that actually executes this linear combination of the data, and you can phase it just like a standard spectrum, and processing that results in the correct data. Given the time, I'm going to speed up a little bit through that. Getting rid of T1 noise. Ideally, you optimize your spectrometer parameters, things like lock, and keep it nice and quiet to minimize that. But should you have some T1 noise, you can get rid of that by selecting a region where you only have noise and no peaks. You expand that. You go under advanced, you find the calculate projections mode. You do an update from the rows and columns. This now says that it gives you the first and the last row of the region you want to calculate the partial projection from. Now this only contains noise, and you can now go into the add subtract menu, enter that projection as second data set, and you click on subtract 1D, and then it subtracts that from your entire spectrum. So every point which is less equal or lower than what you had in the projection is going to be removed. Since this was only noise, all your T1 noise has been eliminated. If we quickly go through peak picking can either be done automatically or interactively. For the automatic one, PP, or you pull it from the menu, it gives you a pop-up window where you can define some of the parameters. Automatic peaking will then pick the entire region. There are a couple of options. One is diagonal gap. If you do a homonuclear 2D, your diagonal is usually of less interest. So you can exclude that. 4 points left and right of the diagonal will be eliminated in this case. And in that case, the peak list looks like this, and the diagonal peaks have not been picked, or to a large extent have not been picked. The interpolation type is another fun. You have two options, is non and parabolic. And in the non mode, it just peaks the maximum point. In the parabolic mode, it does a 4-point parabolic fit over the spectrum. And you can see here that these lines, that the peak actually lines up with the kind of corners in your contours. That is where the actual data point is. Whereas here, it has done an interpolation and really put it to the where the maximum would be if you had higher digital resolution or better definition of your data. In the interactive peak picking and some of the function, I'm just gonna play out here with a little video. You go to manual peak picking, you then get these extra buttons. One of the buttons is defining the peak range. So it helps if you just limit that to the region where you do have peaks. You then execute the peak picking in this range. And here you have the peak list. There are a couple of options. You can delete all the peak picking ranges and start again, or you can define a region where you delete peaks. So here we have a range of peaks which got picked along the residual water signal. And I can simply define this region and then delete the peaks within that region. And at that point, I can save that. Then I can go and inspect the peaks in the peak table. I see all the peaks here. I have the chemical shift in both dimensions, frequency, intensity. I can add more information into those columns. I can sort it according to those different columns. I also have a possibility. The right-hand part of the spectrum is where you can annotate a peak. So here I can then zoom in and I can see I now have an annotated peak. Get out. Why did you just jump? Okay. So here I go back. I can also export the data. It allows you a number of formats, native formats, XEZ, and you can also export the data into comma-separated files and Excel sheets. If we go, you can now read in your data from Excel or from another program which handles this. Oops, that's not what I wanted. So now we go to integration. There we have the exactly same function. We can we can integrate automatically, or we can integrate interactively, and we will see again. You have to start out from a picked spectrum. So in this case here, we have the peak list. We then perform the automatic integration. It asks for a minimum threshold, and it shows you the number of peaks it has. You go through and it performs an automatic peak picking. If the saddle or the lowest point between two peaks is above the threshold, it joins it together. This actually is integration by iterative integration. So it fills data points with let's say columns, and it actually matches the peak shape. So this is a integration which matches the peak shape. If you want to work with interactive integration, you enter the menu and you start out by expanding a region, and you can now define integrals in an interactive way. You draw boxes around your signals. And you can draw a second one. You can choose the mode, whether it's positive only, negative, overall, and so on and so on. So you can do a third one where you can, you then have the option of modifying the box after you've drawn it. So you can make the box larger or smaller or something, or make it match the peak better. You then also have an option to copy peaks. So you can just, so now you choose the copy mode, and in that you can just drag a copy of that box and drop it on another signal. And the remainder one, the last two need a larger box again, so I define a larger box and then copy that larger box onto the last peak in this window. And you can then just, you run the integration, this again generates a table. And if we look at the integrals, we now have the integral values, and for each one, the peaks which are included are listed, et cetera, et cetera. So we have a large set of data available, which we can again export. So let's use the remaining few minutes for 3D. And 3D processing is really not complicated. There were some older commands before, TF3, TF2, and TF1, which were used for 3D processing. Ever since we went to up to 8 dimensions, we didn't want to introduce TF4, etc. So FTND is the universal processing command. 0 does all the dimensions in the order of acquisition. The acquisition order is stored with the data, and it will process in the same order you acquired it. FTND space 3 will do the direct dimension in a 3D, or you can do some of the indirect dimension individually, or you can specify the order in which it should be processed. There is an option, there is an important option to it, and that's called DLP, delayed linear prediction. And you use that when you use linear prediction in multidimensional data more than one dimension. Because linear predicting over a predicted dimension can give interesting results, to say the least. So the proper way of doing this is to process along the acquired dimension with your apotization, your window multiplication, and the Fourier transform. Then you process an indirect dimension without linear predicting. You then process the perpendicular dimension with linear prediction. Then you back transform the one you transformed first, and you do the final processing with linear prediction, apotization, and your Fourier transformation. And that gives you clean data in data sets which have been linear predicted in more than one of the dimensions. Determining phases in a 2D experiment, you don't need to run a 2D for that in a lot of cases, but you can use a 2D plane. If you have nice signal in the echo-anti-echo plane, you use that one. Otherwise, also here, use the EAO option so that it takes the first 2 planes, linear combines that, you do the processing, and you're fine. Little trick I use all the time is when you do this process, it asks you here into which process number you want to store the 2D data. I always use the dimensions for that. So the 1,3 direction goes into Prochno 13, and 2,3 goes into 23. And if I do a 40, it goes into 1,4 and 2,4 and so on and so on. So I remember later what I've done. Maybe you only have to do that when you're a bit older. So if you use the echo-anti-echo plane, processing is very simple. If you don't do the EAO option, for example, a proton-carbon dimension in HNCA would be 90 degrees off. But if you use the EAO option, you can easily just phase it like a regular spectrum, store that back into the 3D, and you're good. The baseline correction commands, to a large extent, are also available in 3D, so you can process that as well. Again, this is probably more an educational aspect of the processing, but you can break it out into the individual steps. So if you have a 3D data set, if you do a FDND3, that processes along the acquired dimension only. So now you have no zero filling yet. So you have a nice little cube or box of data in which are the spectra, the F3 dimension. If I follow that with the FTND2, I now have processed along 2 dimensions. In this case here, I have a HN type experiment. I guess it's an HNCA. And the projection of that, it looks like an HSQC. And I see decaying signal in the carbon dimension because I have not Fourier transformed in that dimension yet. If I turn that the right way, there are either stalagmites or stalactites in a cave. And I think there are lots of caves in the Appalachian, not far away from Nashville to visit. Not now. And then the final FDND1 processes that into your standard 3D data set. NUS acquired data, you can do XF2ND2D, and this transforms the entire 3D experiment into one 2D matrix. So this is my 3D processed into a 2-dimensional plane. What you also can do for NUS data, you can take the command NUSFT. So FTND3 NUSFT puts all the data into the right place, into the grid. So when I actually look at a F1, F2 projection of my data, I see these, every spectrum I generated makes one dot here. And amazingly enough, if I compare that to my NUS list or my acquisition schedule, that's exactly what it looks like. So I have these 2 points here and I have these 3 which are arranged in a triangle right here. If I would process that without reconstruction, I of course get a very noisy spectrum, but it's now if I do an FTND3 on NUS data, it starts filling in, it does direct reconstruction as part of this operation. So in just the regular way, I type FTND0 and I get the data done completely in one single step. And with that, and in time, basically, I come to the end of my presentation here. I would like to thank you all for the attention during those last 45 minutes. I would also like to make you aware of the webinars we have been doing since May. First, when everything was locked down, on a very intense schedule of 3 webinars a week. And then we have started thinning them out as people have slowly eased back into, well, the new normal, to say the least. We've just recently posted the schedule, which we are now doing more webinars, 1 every other week until the end of the year. All the webinars we've done are recorded and are out there for you to enjoy if you have the time to do that. A good portion of what I just presented was in my advanced processing webinar. We have QNMR webinars, we have solid state webinars, we have on all kinds of topics. The link is right here. You should be able to find that relatively easy on the Bruker website again. And with that, I think we're heading on to the Q&A if there is anything. So I'm happy to answer any questions you might have.
Thank you so much, Clemens. This was very helpful. And we do have a a couple of questions. The first one basically pertains to the linear prediction. And that was what parameter needs to be set up for backward linear prediction?
Okay, if you do backward linear prediction, we're using a set of the same parameters. So backward linear prediction, you use LP-bin is the number of input points. So this is the number of actually acquired points you're going to use for the prediction. You use the number of coefficients, NCOEF. I think in other programs it's called number of poles or something like that. You use those, and then the TD off parameter, TDOFF. If it is a positive number, you overwrite existing data points with predicted points. If it's a negative number, you prepend data points to the data. So you extend into negative time when you use when TD off is negative. So I mentioned the W's. LP-bin is used as points to predict out if you're doing a forward linear prediction. If you actually want to combine backwards and forwards for one data set, that's where you have to use this XTRF commands, where you first set up for usually the backwards prediction first, and then you change those parameters around. You do the forward prediction combined with the Fourier transform.
Yeah, that is good. And if there needs to be a follow-up, I think the user could probably contact you for the specifics on it. Huh?
Sure, absolutely.
Right, because there's a lot of information, a lot of parameters that are involved in those processes, backward and forward prediction. So yeah.
Okay.
It is pretty simple.
It's not hard. It's not hard. I see a second, I actually see the questions here. So I see a second question. In the Bruker website, it is written that complete NMR software package in a new cost-effective and affordable combination. So for academic, governmental, and nonprofit users, TopSpin is free. Everything which is part of TopSpin is free. That, for example, includes programs like NMR Sim. It also uses the BioTop, the biomolecular setup software. It's no longer free when you go to programs like reconstruction of non-uniformly sampled data. The free version is 2D with basic iterative soft thresholding algorithm only. Since we licensing the software from a third party, they decide what's free and what's not. So 3D and higher and the advanced algorithms, they're not free. In the software, there are a couple of other packages which are not free, which you need licenses for, from structure elucidation but there are many other packages which are free. And I see there are also questions in the chat.
There's one in particularly, yeah.
Yeah.
You want to read it or?
Okay. Could you comment on the real necessity of acquiring 1D13 spectra? Not to mention my group is focused on natural products chemistry, and some of our colleagues still collect 13C data of everything beforehand. I would be afraid to step into a minefield if I take sides on this. My view is there is a danger in two-dimensional spectra. The absence of a peak does not necessarily mean the absence of a carbon or a signal there. There are conditions where the 2D spectra don't give you a peak. because the coupling constant is very small. It's far away from the nearest proton. I mean, the HSQC is pretty straightforward, even though I've seen cases where signals got lost even there. So the properly acquired 1D spectrum is probably still the gold standard in terms of determining the number of carbons in an unknown molecule. So I would not completely do away with doing the 1D. If your 2D spectrum, I mean, considering that generally you need the molecular formula before you start doing NMR. So the joke goes, what's your first NMR spectrum? It's a high resolution mass spec. Considering that you know the carbon count, if your HSQC and HMBC is in agreement with the carbon count in your molecular formula, you can probably get away from doing a 1D carbon.
I guess there is certainly also the issue of HSQCs versus HMBCs for the quaternaries and all those questions that need to be considered.
Yeah. I mean, in the HMBC, it's really a question I've seen. There are many molecules out there where there are extended networks on quaternary carbons. And once your quaternary carbon is isolated by 4 or 5 bonds from the nearest proton, it becomes close to impossible to find those, or it becomes very difficult. The other case where I had issues were neighboring nitrogens, which made the signal so broad that it was barely visible. And these things, so with a huge grain of salt that has to be taken.
Right, right.
All right.
There has been a hand raised, but I think the listener may have withdrawn.
Yeah.
But if there's any other question, you can raise your hand right now or put it into the Q&A. And if we don't see any other questions, you certainly can, I'm pretty sure you can contact Clemens directly.
Sure.
Look at the tutorials. These tutorials are really helpful. They have a lot of information. And as I said before, you can kind of stop them and go to your NMR program and practice it and see what it actually does.
Yeah.
Set. So
I actually also seen the question you answered, Marcus. Yes, I can make the slides. I can make a PDF available. Okay, good. I can do that. So that'd be great. So because if they're interested in one slide, if you don't have a fast forward, it can be hard. But yeah, I can make those slides available. There's nothing secret in them. Good, good. Well, if there is no other question, I really would like to thank you, Clemens, for this wonderful presentation. Very helpful. You're most welcome. And I think it's a lot to digest, and people should just go ahead and try it out and see exactly what they can get with it. It's processing only. You cannot break an instrument with processing only. So you can try whatever you want. You can do it even at home. Exactly. Yeah. Thank you so much. Appreciate it. You're welcome.